Howdy, everyone. I hope you're all doing well and staying healthy despite the crazy times we've had. I've been in College Station more than 50 years, and that was the worst storm and coldest weather we've ever had. On top of that, we still have the virus kicking around. You should have all seen that we've delayed the exam until a week from Wednesday, and we'll have a review for the exam this Friday. So 2 class days before that. Are there any logistical questions? Also the problem sets, I encourage you to turn them in as soon as you can so you have time for study. But if you turn them in as late as this Friday, that's still okay. Any questions on any of that? Okay, I thought I'd show you a few little posters that people are putting around. Many of you have not had a chance to be much on campus, and so maybe you're missing little strips of paper that people put up. So you start with a lost cloud, but then a lot of people put up little signs like this. This one's not much, but anyway, someone didn't like his bike or her bike. Someone sent a chat question about the symmetry stuff. Since I wasn't able to get into my office, I had to take what I had. And so obviously we aren't covering symmetry in this course, so you're not responsible for that. Just for the review, look at the first set of material. Unfortunately, the Copy Center failed to include those problems in that set, and I didn't have a chance to check that over. Someone asked if there's a practice problem set for the atomic stuff. And yes, and that was included in what I sent you. The first part is quantum mechanics. If you go through the answers, you'll see something that says more practice problems, and it includes 1 or 2 problems having to do with atomic systems. Also, the quantum mechanics section, it includes wave functions for the hydrogen atom. And so some of that is covered in those review questions also. Okay, we're running out of flyers here. This one. And I think this is a nice one to end on. Okay, so with all the lectures that we have had, we have covered everything that's going to be on the first exam. And as I said, we'll review for this Friday. Before I get into new material, I want to tell you a little bit about the universe. A lot of this, hopefully, you already know. But I just want to show you and remind you what an important role the hydrogen atom spectra have played in helping us understand the universe. If you haven't seen this before, this is one of the most famous astronomical pictures ever taken. It was taken over a decade of time. Here's what the explanation is. The image that is showing represents less than 1% the size of the moon in the sky, and it's a very dark region of space that you probably see nothing with a naked eye. But it took more than a decade, hundreds of long exposures, and what you see in this picture with this tiny, tiny, tiny portion of the sky, you see 10,000 galaxies. So you can't quite tell they're all galaxies, but you can see most galaxies are kind of spiral and flat, and so this one and that one are pretty easy to tell. Some of these galaxies are more than 10 billion light years away. So the light that was observed here started more than 10 billion years ago. And of course, we have an expanding universe. And the reason we know we have an expanding universe is because we understand the hydrogen atom spectra and the Doppler effect that it has on it. So I don't forget to tell you the current estimate of how many galaxies we have in the universe is 2 trillion. So that's 2 times 10 to the 12th. The Milky Way and Andromeda galaxies each have something like 200 billion stars in them. And so, you know, if you make a modest estimate and say each of those 2 trillion galaxies has 100 billion stars, that would be about 10 to the 11th. You come up with something like an Avogadro's number of stars in the universe. And many of these may have 5 to 10 planets around them. And sometime later, maybe I'll tell you what my opinion is about life in the universe. But it would be crazy to think that there aren't at least thousands, maybe even billions of planets with intelligent life currently in the universe just from these numbers. So as I said, a lot of this we know because of the hydrogen atom spectrum. Most of you, I think, know about the Big Bang Theory. I don't know how much you read about it in detail, but just as a reminder, our sun and all these stars we're looking at has a lot of nuclear stuff. It's been estimated the core is maybe at 30 million degrees. Out towards the outside, it drops to maybe a few tens of thousands of degrees. And the most common elements and entities in the universe are hydrogen atoms and helium atoms. There's lots more hydrogen atoms. It's the simplest thing to make, obviously. And the hydrogen atoms exist outside of stars. And so when a sun or a star emits light, then the hydrogen is out there to absorb it. So we can say white light is emitted by the sun or stars, and then where hydrogen and helium have their spectra, those lines are absorbed. So for example, if you were looking at our sun, you would see that there is less light coming at 24,380 wave numbers, which is the N2 to 6 Balmer line in the hydrogen spectrum. And then there are lots of other lines. So we know that it's hydrogen that we're looking at because we've looked at this on planet Earth. We had to split up the H2 to make hydrogen atoms. Okay, so what happens in the universe when we have an expanding universe? Some of those galaxies we just looked at are approaching the speed of light in terms of expanding away from us. So some might be going at, say, 9/10 the speed of light away from us. So unfortunately, I don't have a nice way of making this straight. But what the dark figures and the white lines on them, this is a normal spectrum on a photographic plate of a hydrogen atom. When we're looking at an object that is moving very rapidly away from us, then the apparent observed frequency that we see is given by this formula right here. Frequency times 1 minus the velocity of our star that we're looking at divided by the speed of light. The same formula works for sound, except instead of the speed of light, you would have the speed of sound. So I think you're all aware of an ambulance coming at you. It'll have a higher pitch siren than when it's going away from you. You see a lower pitch. But here we're looking at what's called a redshift. That means we're shifting to lower visible light. Red is on the low energy end of the spectrum. Anyway, what I'll try to depict, these lines are the normal spectrum of hydrogen. But what happens when you have the expanding universe and you look at something going away from you, each of these lines is shifted by a certain amount. And I've just shown you a few of these, but what I want to emphasize is you can still be sure it's hydrogen because all of them follow the same formula that we have here. So when astronomers and astrophysicists look at the universe, they can look at stars and objects, and they have special methods for telling how far away an object is. But then, thanks to the hydrogen atom spectrum, we can tell how fast it's moving. And if you back calculate where pretty much everything was, you find that 13.8 billion years ago, everything was pretty much in one spot. Now, theoretical physicists are totally convinced that the whole universe was smaller than a BB in a BB gun or a pea or something like that, just incredibly small. And in fact, there was no matter at all. It was all in the form of photons. Photons, delta E is equal to h nu. These photons were at incredibly high frequencies, but the whole universe was there. And then it all started 13.79 billion years ago. Nobody has a clue what really was before that. People such as I like symmetry, so I like to think if we have a big bang and the universe expands, at some point it'll start contracting. You will have a big crunch, everything comes back together again, and then we can have another big bang and keep the universe going. The latest thinking by astrophysicists is that, in fact, the expansion is increasing its speed due to unknown phenomena, things like dark energy and dark matter and stuff like that. Anyway, my reason for showing you this is I think this is the most incredible scientific story there is. We take the smallest chemical entity we have, the hydrogen atom, and this is the clue to understanding what the universe is all about, namely the largest thing that we absolutely have. If you read more about this, then you'll know that there was a radio astronomy experiment at Bell Laboratories in the 1960s, and they recorded a predicted residual microwave signal in space, confirming what the temperature of space would be if this Big Bang model worked, and it exactly matched. These radio astronomers weren't actually even looking for it, but they found it and they got themselves a Nobel Prize for doing it. A few people had maybe conflicts with religion and the concept of a Big Bang. It was actually a Catholic priest, I think in Belgium, named Lamontre, who first postulated the Big Bang theory, that we had an expanding universe. And so you don't necessarily have to have conflicts with what your beliefs might be. Anyway, I get very excited about this. A lot of spectroscopists like me find astrophysics, astronomical things to look at really fantastic. Okay, so let's see where we are. Okay, our new topic now goes to molecular structure. This will not be on our exam next week, but a lot of the stuff we talked about will be based on quantum mechanics, so it's good if you try to follow through as we talk about this, as some of this can apply to questions we might have on the exam. First broad topic I want to talk about is called the Bourne Oppenheimer approximation. And we've already alluded to this before, but we're going to find that this is our excuse for looking at electron energies when we talk about atoms or when we talk about molecules. We're not going to worry about nuclear energies. We're going to say electron energies are separate, and that's the main thing we care about. So let me just show you where this comes from. Oppenheimer, by the way, I think he was a student of Max Born's. He was also the fellow at Los Alamos National Laboratories in New Mexico that headed up the atomic bomb project where the US developed the atomic bomb that ultimately was dropped in two places in Japan. But he was working on some of these theoretical aspects before. Okay, so basically, uh, uh, just a repetition of what we've been saying. Our Schrodinger equation can be written as H psi is equal to E psi, and our Hamiltonian looks like this for one particle. And what we've been saying is that we can calculate all the information that we can possibly know if we solve this problem. Heisenberg comes along and he says, well, we can't quite know everything. But I want to start off and show you that even simplest cases can be very complicated. So the simplest molecule that we can have, if we can even call it a molecule, it's a molecular ion, is H2 plus. So we're going to have two hydrogen nuclei. We'll have one electron. This species actually exists. It's been studied on Earth. It's very reactive, but we've gotten spectra of it. We know it's what its energy levels are, and so on. So everything we say about it has been confirmed experimentally. Now, based on everything we've been saying, you should be able to write the potential energy for this. The potential energy, you'll remember, is the product of the charges divided by the distance between them. So this plus charge attracts this negative electron. This has a charge of plus E, the electron charge. The electron has a charge of minus E, so the product is minus E squared. And if you divide by the distance between them, that's the attractive potential energy that this proton has for this electron. Okay, well, the second proton attracts it the same way. So we have minus E squared over RB with the distance between them. And then the two protons repel each other. That's plus E squared over RAB. Plus E times plus E gives us plus E squared. All right, so if we wanted to do the complete problem, this is a three-body problem. Physicists already groan at three-body problems. They say that's two particles too many. But we'll start off with this. We have a kinetic energy term for the electron. We have a kinetic energy term for proton A. And then we have a kinetic energy term for hydrogen nucleus B, which of course is the proton. And then plus V again. Okay, so if we solve this, then again, we can get all of the energy levels and all the wave functions. But as I said, we're going to focus on electron energies. And so this is what the Bourne-Oppenheimer approximation is. It was demonstrated that electron motion is so fast compared to the nuclei that the nuclei can be assumed to be still. So this means if we look at these kinetic energy terms, the kinetic energy of the protons is going to be so much less than for the electron that these are negligible compared to this del sub E for the electron term. The other thing to note is that we have this mass of the proton in the denominator, and the proton is 1,832 times heavier than an electron, so that further makes these terms smaller. So basically, Bourne and Oppenheimer says, we throw these two kinetic energy terms for the protons out, and we solve the problem just for the single electron when we're doing the H2 plus problem. So their paper obviously was a lot more complicated, many pages. They said that the overall wave function can be separated into a nuclear part. And this does not mean atomic bomb energies or things like that, but nuclear motions like vibrations and rotations of the nuclei. And then there's an electronic part. And if you look at the electronic part, you'll see it'll still have this capital D potential energy in it, and it still depends on the distance between the two protons that we have. Okay, so this is the problem that in general we're going to solve for the H2 plus molecular ion. When we get to larger systems, I'm not going to go into so much detail, but it's basically going to follow the same kind of model. it's going to follow the same kind of model as we're going through for H2 plus. Now, all of you noticed, of course, we just lost a week of classes, and we're not changing final exams or anything else like that. So we're going to need to condense some of the material in our lectures. And I don't think you'll mind the parts that I'm just going to condense some of the mathematical parts into things that are smaller. Also, I don't think you'll mind we're not going to have a first pop quiz, which would have taken part of the period. So there won't be a pop quiz before our exam next Wednesday. Okay, so this next part, I'm going to show you what we're going to basically do, but then on the mathematical steps, I'll just basically, on the mathematical parts, I'm basically going to just ask you to look at them at home and say that it's something, again, that you'd be able to understand if you want to go through the detail. Okay, well, our method for understanding molecular bonding, it's going to be called molecular orbital theory, or MO. And the side caption is we're going to talk about linear combinations of atomic orbitals, or LCAOs. And we're going to start off with diatomic molecules. So the H2 plus could be considered a diatomic ion. And we'll see how the bonding works. And once we understand that, then it'll be a little bit easier to talk about some larger bonding systems and explain how these things correlate. Everything we're going to do is going to be based on the variation method, also called the variational method. And you'll remember this method basically says we start with a trial function that will apply to a quantum mechanical problem. And we try to get the lowest energy possible because the trial function will always give us an energy that is larger than the real value. And as I've said many times, computers now can get these answers right to within 7 or 8 decimal places. For the H2 plus, it can basically do this accurately. Okay, so what kind of function should we choose for H2 plus bonding? And so a logical thing is we're going to make linear combination of atomic orbitals. We'll take the 1s orbital on nucleus A and the 1s orbital on nucleus B. And let me remind you, you know exactly what these are. These were the solutions that I gave you for the hydrogen atom 1s orbital. Basically, it was e to the minus r over a naught, where a naught was the distance from the electron to the nucleus. Okay, well, to this then we're going to add with a coefficient a certain amount of the orbital from nucleus B. This is kind of a trivial example, so when we're done, we're actually going to see that these constants are going to be either +1 or -1, but I want to show you how the mathematics works. I'm going to be changing nomenclature quite a lot, so we get tired of writing these psi's to begin with. So just to simplify what psi subscript 1sa is, for the time being, I'm going to call it 1sa. So the 1s orbital on nucleus A, and then psi 1sb will be the one on 1sb. Okay, so this is our trial function. We stick it in the variation term. When we want to see how well this works to telling us where the electron is going to be, we want to have a probability function, and the probability is always the wave function squared. So that's what this comes out to be. And what you'll see is we get 3 terms. We get this term squared, and then a cross term. This first term is exactly the probability that an electron would have on a hydrogen atom if it's on nucleus A. This is the probability that it would have if it's on nucleus B. And then this is a mathematical cross term. Parenthetically, I've said, notice that 1s and 1sb are not orthogonal because they are wave functions on different atoms that we have. So if you worry about multiplying them together and integrating them over all space or something, then you don't have to worry about orthogonality. But the thing I want to show you is, well, what I would like to show you is this in three-dimensional space, but we only have a two-dimensional screen. And so I've got a representation of psi squared here versus where the atoms A and B are. And then I'm showing you the probability. So the first term will have the highest probability about nucleus A. Second term will have the highest probability about nucleus B. But the middle term puts probability in between the two. Now remember, whenever we have probability, that means we have negative charge. So we're talking about where an electron is going to be. So if we add this all together, this is what we expect for the electron probability distribution. We have one simple little electron, but it's flying all over the place. And a lot of the time, it's going to be between the two positive nuclei, and that's where a chemical bond is going to come from. Seems pretty simple-minded. It's kind of like a Lewis structure in freshman chemistry. You put two dots between a couple of atoms for a bond. Here we have would have one dot for the H2 plus ion. But this is basically the picture. This is what's keeping the nuclei together. Plus charges would repel each other, but if you put negative charge in between, the plus charges are attracted towards the center. So this is going to be the physical picture of our chemical bond. So now let's look at the mathematics, and this is what I'm going to skip over. This is the formula for calculating the energy from a trial function from the variation method. So the first thing is you do the Hamiltonian on our trial function. This is our trial function. Then you multiply it times the function. You solve that integral. And in the denominator, you just take the square of the trial function that you have. Again, to save time, I'll just point out you get integrals that look like this. Let's just have the A terms or just the B terms. You'll get some cross terms with A and B. And in the denominator, you'll get something that looks like that. So we will name all of these things, and we can calculate our energy in terms of these different integrals. So all of these typically are going to be integrals that you cannot solve exactly. You have to go to numerical methods. And that's why we need big computers to numerically solve lots and lots and lots of integrals when we're trying to get the best energies that we can from trial functions. Okay, the next part I'm going to go over fast again. Integral HAA looks like this. Notice it's got the kinetic energy term and the potential term for just hydrogen atom A. And so this will allow us to pull out the energy of a hydrogen atom from it. Then we're going to have some other cross terms. And when we make these combinations, we'll get the E sub h, the energy of the hydrogen atom. We'll get an integral that looks like this, called the Coulomb integral. And then we're going to get E squared over RAB. You remember in the Bourne Oppenheimer approximation, we said that the nuclei are big and fat and sluggish and they hardly move. So as far as the electron is concerned, capital R, the distance between the two electrons is fixed. All right, so this allows us to write this integral as E sub h plus j plus E squared over RAB. We do a similar thing for HAB, note some things, make some combination, and we find what it comes out to be. And when we finally get done, the energy for our trial function, which we know has to be at least a little bit larger than the actual energy, comes out looking like this. E sub h we know from solutions to the hydrogen atom. And then J and K we have to solve for numerically. E squared over RAB we can solve as a function of what the nuclear distance is. Okay, so we want this to be as small as possible. And you remember our trial function had the coefficients C sub A and C sub B in it. And so we will take derivatives of the energy with respect to each of these coefficients. We'll get two simultaneous equations. We will solve them after we set up a determinant called the secular equation. And we get formulas for EG and EU. These are the two possible energy levels we can get for this problem. And we find what our coefficients come out to be. The stuff right here is a normalization constant. CB here has the minus sign in front, but it's also the normalization constant that you have. Okay, so the details here are just mathematical, and normally I think it'd be good if you could appreciate where it comes from. But the key to this is that if we're looking at two coefficients that we have to solve for energies, we get two simultaneous equations. We minimize the energy, and that will give us a pretty good result. If you remember from way back when we actually met and I looked at the variation theorem, we looked at a trial function for a particle in a box. And when we had two parameters that we could vary, we got accuracy within something like 0.000%. So this is a terrific numerical method that gives us nearly perfect answers. Okay, well, here are the important points. So we're going to get one energy solution. Again, this is the energy for a molecular orbital into which you can put an electron. One energy will be E sub H plus the repulsive term between the two nuclei. And then we have a term of involving the different integrals that we have to solve numerically. Anytime we start from two atomic orbitals, we have to wind up with two molecular orbitals. And it turns out we get a second orbital, and this one we're going to call an antibonding orbital, because this is actually going to hurt bonding if we put electrons into it. The wave function for the first one looks like this. In other words, we just had a plus sign between 1SA and 1SB, and then a normalization constant. And I apologize, but I didn't have a chance to get this corrected in my notes. Make sure you correct this. This should be 1SA minus 1SB as the molecular orbital that we have for the second case. And I'll show you pictures of these in just a couple of minutes. Okay, well, first of all, we get two formulas for energy. For the H2 plus molecular ion that we're looking at, we have one electron, so it's going to go into its lowest energy orbital, E sub G, and the actual energy is going to have to be lower than E sub H in order to create bonding. So if we start with an electron on a hydrogen atom, and it has to go into a molecule, it has to become more stable to form the molecule. Okay, there's a question about ionic bonds and covalent bonds. We're going to get into some of that later, so I'll come back to that further on. Anyway, so here's a graph of what E sub G, the energy of the molecular orbital, would be as a function of the distance between the two nuclei. So look at this formula here, and you can see that if R gets to be very small, then this is going to become very large. So if R gets very small, you're trying to crunch the two nuclei into each other, and the energy practically approaches infinite energy. So the two nuclei do not want to be very close together. On the other hand, Integrals J and K will get to be more negative. They're already negative, but they'll get to be more and more negative, overcome the repulsive force as you increase your R value. So at some point, you're going to hit a minimum energy, and that's the bond distance that the molecule is going to choose to create the bond. So we can assume that this is going to be something like half an angstrom or so, that the two nuclei wind up apart. The electron will go to a molecular orbital of this energy, and that's what it will choose for its structure. If we go to higher R, those integrals J and K get to be less and less, and at some point, the energy approaches that of the hydrogen atom, because you're pulling the electron totally away from it. So as long as we're below E sub H, we're creating a chemical bond, we're stabilizing that electron. Now, you may or may not have seen something about antibonding orbitals in organic chemistry. I think it depends on your professor. But a big aspect of molecular orbital theory, and this is backed up by experiments, is every time you form bonding orbitals, you also form antibonding orbitals. So here's the form of the energy for the antibonding orbital, E sub U. The U, by the way, stands for ungerade, the German word for uneven. And if we had the minus sign here, 1SA minus 1SB correctly, then that's why we call this an uneven orbital. The G stood for gerade, or even, so with a plus sign that we have here. Anyway, the antibonding orbital, because this term is always repulsive, and because the integral K, which is the most important for bonding, is always negative, this will overwhelm the E sub H, and we will always have a positive value for E sub U. So what happens in the molecule is you form this orbital where I've got the dotted line, but you also form the EU, and I didn't extend the dotted line there. That orbital will exist, but it will not have any electrons in it. But if we did put electrons in it, they would be antibonding and be opposed to bonding. Okay, so here's the important thing about where bonding comes from. 90% of the stability of the chemical bond of H2 plus, and this will also be true when we get to larger diatomic molecules, larger molecules, comes from the resonance integral. And mathematically, this is what it looks like. So if you try to understand what this means, we have one wave function representing an electron on A, one function representing an electron on B, and then there's an attractive term, and the first integral here represents attraction by nucleus A. So only nucleus A is attracting it. But the important thing is that both of the nuclei are having probability to give us value for this integral. If 1SB were totally missing and the integral were 0, then the resonance integral would go to 0 and we would not have bond. Well, this is exactly the same if we have the electron attracted by B. So this term also shows up in the calculation of the energy. So physically, we can say the system is stabilized by the electron being allowed to be on either nucleus. So we call this a resonance between A and B. In organic chemistry, you learn about resonance structures for benzene. You draw double bonds in different places. The molecule doesn't really flip them back and forth. The way I like to draw the benzene ring is just a circle in the center. They're all sort of 1.5 bonds. And this is kind of the situation here. The electron is neither, or it's not only attracted by A, or it's not only attracted by B, but both of these terms come into play. The other contribution to bonding, this is called the Coulomb integral, and it has this form. Both of the wave functions come from nucleus A here, but the electron is attracted by B. So here's the physical picture. Here's nucleus A. Its electron is going around it just like it's a hydrogen atom. But B is over here with its plus charge, and it's attracting it. So that tends to keep the two nuclei together to some extent, but not nearly as much as this resonance in it. Mathematically, we have also a similar representation right here. Okay, so I've gone over this much more rapidly than I would have liked, but the key element is be familiar with this diagram here and why it is the way it is. We do expect potential energy to go to infinity as the bond distance between the two positive charges gets very small. But because the integrals j and k are negative, we can find an ideal value for those integrals. In other words, maximum negative values, which will give us our most stable situation of the molecular bond. Okay, so this I once had as a transparency that I showed in class, so that's why it's in this particular format. I want to say just a little bit more about the resonance integral. So mathematically, it looks like this. And remember that if you have in an integral the product of three functions, we don't have any derivatives or anything else like that in here. All three of these terms have to be non-zero at the same time. If any one of these terms is zero, the whole integral vanishes. So if we look at each of these terms, this is basically 1SA. Again, I'm trying to draw a three-dimensional picture in two-dimensional space. This is 1SB. It has a maximum about nucleus B. 1SA has a maximum about nucleus A. And then this attractive term, minus C squared over RA, looks like that. And fortunately, all three of these curves have positive value right in between the two nuclei. So when you're actually solving the integral, it winds up looking like this. And so an integral is the area under the curve. And you'll see this represents an area, or more technically a volume if we're in three-dimensional space. It represents an area where you can have probability of negative charge between the two positive nuclei, and this is your chemical bond. So all three functions have to be non-zero to contribute. Okay, so if a lot of that kind of went by you, I think it's even more important to just visualize what is going on. So here's basically what we did. We took a 1SA orbital, we took a 1SB orbital, we smushed them together. My curly Q lines here represent where the electron is flying around. The important part is we get electron density minus charge between these two positive charges. That is our chemical bond that we have right here. Okay, this we could do because the wave function did not change sign. We had 1SA plus 1SB. So we went from plus wave function to plus wave function. In my notes, I made a mistake. I had 1SA plus 1SB for the Ungerade antibonding orbital. It should be 1SA minus 1SB. So the wave function on the left is positive. It has to go through zero and become negative on the right. So we're going to have a region of zero probability and very low probability for the electron between the two positive nuclei. And so you can see you'd have a lot of repulsion between them. And so any electron you try to put into this orbital will be repulsive or antibonded. So a lot of people at this point have the reaction, well, we don't want antibonding orbitals, why talk about them? Well, they do exist, and we will see for many systems that it helps understand molecular structures and electronic spectroscopy and colors in the universe and all kinds of things like this. So antibonding orbitals do exist. The H2 plus molecule does not want to put an electron in there. It would fall apart if it went there. It's happy to have its electron in this bonding orbit. Okay, so that's our simplest model that we could have. We have just a little bit of time left, so let's go to the first real full molecule we could have. Two nuclei and two electrons, the hydrogen molecule, and we have all of these distances between the charged particles. Attractive forces come up with minus signs. A plus E proton attracts a minus E electron, so it's minus E squared, and you divide by the distance between them. So the first term, minus E squared over R1A, is the attraction here. The second term is the attraction for the first electron by nucleus B, and all the minus signs are attractions by the nuclei for the electrons. We have a repulsion between the two electrons, plus E squared over R12, minus E times minus E gives us plus E squared over R12. And we have a repulsion between the two nuclei right here. So make sure that you're able to write a potential function for simple systems like this. Now, if we didn't have Bourne and Oppenheimer, we would have to have a four-particle problem, but we're going to stick to just electrons. So we're to just consider electron 1 and electron 2. We're going to say we can ignore the energies of the nuclei, but later when we talk about molecular vibrations, we can have the two nuclei vibrating relative to each other. Okay, so the overall Hamiltonian is a kinetic energy term for electron 1 and an electron kinetic energy term for electron 2 plus the potential energy. So this is what we expect to utilize when we go to the variation theorem and use a trial function. So the question is, what do we use for trial functions? And we may not get to it today, but this is where we can talk about covalent and ionic bonds. But let's just throw out some possible trial functions. So here's the nomenclature I'm going to use. When I write 1s sub a of 1, that means I'm going to put electron 1 on nucleus A, and that will represent an atomic function that I'm using as part of my trial function. So mathematically, we know exactly what it looks like. So this is what we had if this were just a complete hydrogen atom itself. You remember we had we had e to the minus r over a naught. But since the distance here is RA1 or R1A, we write it this way. Okay, so 1sb would be the same, except we put electron 2 on B. So what happens if we try this as a trial function? Well, we would get a terrible result. It would be way, way, way higher in energy than what the H2 electron would be in its orbital. And hopefully you all recognize why that's the case. It's much too restrictive. It means electron 1 has to stick to A, electron 2 has to stick to B. They're now not allowed to go back and forth. Okay, so let's try a better function. So this is the same as we had, but let's now reverse them. And this would be what's called the valence bond function. So this would be a covalent bond representation. 1 on A, 2 on B, or switch them around, 2 on A, 1 on B. So we have a sharing of a pair of electrons. All right, well, in the 1 minute I have left, let me point out that we do have to worry about ionic possibilities. So here's an ionic possibility. 1sa of 1, 1sa of 2 means both electrons are on nucleus A. And then 1sb of 1, 1sb of 2 represents that they're both on B. Notice that we're just adding a whole bunch of possibilities here. So we have 1, 2, 3, 4 possibilities. And we want to look at this as maybe being our best trial function when we start. So this is what we now have, and we're conveniently running out of time. You'll notice we have a covalent part, and then these terms are ionic. So the first case here would have both electrons on A, so we'd have HA minus, HB plus. Nucleus A would have a plus charge and 2 electrons. Nucleus B would only have the plus charge. If we put them both on B, then we'd have the ionic form HA plus, HB minus. Now, if you're really sharp and you're thinking about it, you're going to say, wait a minute, shouldn't the covalent part be more important than the ionic part? And I would say, yes, you're absolutely correct. So if we wanted our best function, this is what we would do. We would put different coefficients for the covalent part and the ionic part and make the covalent part greater. So what we've done today is I've just kind of wanted to show you what the basis is for doing linear combinations of atomic orbitals. So far, we're only combining the 1s orbitals on 2 hydrogen atoms. I'm showing you how the variational theorem can work for figuring out the energies, and I'm showing you how you choose trial functions to come up with best models. If you're worried that this might be too simplistic in computer programs that are run, a lot of times one throws in thousands of orbitals to come up with one molecular orbital. So that way you can adjust a lot of coefficients and get yourself down to the lowest possible energy that mathematics will allow. Okay, so we'll stop here today. I don't see any chats, but I'll hang on for a couple of minutes in case we have questions. If you signed in late and hopefully you got the emails, our first exam is a week from Wednesday. We'll have the review for the exam this Friday. Turn in your problem set as quickly as you can, but you can turn it in as late as this Friday if you need to. Any questions? Okay, hopefully we don't have any more surprises this semester like we did with the weather.